Hi AP guys, this is Mr. Ward. We're going to do some problems, special requests. But first I want to welcome you to Physics Coach YouTube. Okay, first problem I want to take a look at. If I can find my pen. Okay, here it is. Problem number 17, chapter 6. And what this problem says is an initially stationary box of sand is to be pulled across the floor by means of a cable in which the tension should not exceed 1100 newtons. So this would be tension max equals 1100 newtons. The coefficient of static friction between the box and floor is 0.35, so mu static equals 0.35. What should be the angle between the cable and the horizontal in order to pull the greatest amount of sand? So theta equals, we don't know. And I guess we'll call this theta max, meaning theta when we pull the maximum sand. And at that point, or at that angle, what is the weight of the sand in the box? And that would be in newtons. Okay, first thing we need is free body diagram. So here's the box, and here's the weight of the box. And one of our old favorite problems was the situation where we had a rope pulling the box at an angle. So this would be the tension. And what happens there is that the tension's vertical component is about that long. So what that means is that the total of the normal, which would usually be up here by this red dot, would be that long approximately, is going to be decreased by this amount right here. So I'm going to erase those dots, and then I'm going to draw in the actual normal force, which would only be that long. I kind of missed. Okay, so this would be the normal. So to check that, this component of the tension is the blue line. If we stick that up here, then this upward force and this downward force should be the same. Okay, so we get rid of those. And we need one more thing because this is, after all, a friction problem. So we're going to be able to pull this thing with the greatest possible amount of sand. And the assumption here would be that the thing is not accelerating. Doesn't say anything about that, but we'll say this would be the kinetic friction force. Whoops, I'm sorry, the static friction force. So this would be F static max, I guess. And that would be our free body diagram. So let's box it. And of course the acceleration, they just want to know when it breaks loose, it sounds like. So the acceleration here would be 0 in all directions. Okay, next thing we need to do is to modify this diagram to make it a little bit more useful. So what we're going to have here, the tension x component, this would be ftx, which we could also call ft cosine theta. And then the normal force would be the one that we drew. But we also, let's do it the other way. Let's put the vertical component of the tension, which would be about that big. This would be fty, or ft sine theta. I wouldn't suggest putting both of these on your diagram. It's going to get a little crowded. And then on top of that, we're going to put the remaining reduced normal force, because we're pulling up with the rope somewhat, so the floor only has to push up with a partial normal force. Okay, down, of course, that's going to be the weight of the box and the sand, and then our F static max is going to be this guy over here. Okay, so this is our modified diagram, and of course still the acceleration is going to be 0. Okay, so the next thing we need to do, of course, is to take our green diagram and apply Newton's second law to it. I'll put this over here. So the sum of the forces equals ma. And we have two directions to look at. So let's look at the y direction first. So what we would see, calling up positive, we'd have F normal plus Ft sine theta minus mg equals, this is going to be 0. There's no vertical acceleration, of course. And that gives us our equation for the y direction. Now, what are we going to do with that equation? Well, we want to solve for the normal force because this is the friction problem, and that's pretty much what you always need to do. So mg minus ft sine theta. So we're going to be using that in a little while. Okay. Normally I would ask, anybody have any questions on that? If you do, I would put a question mark in your notes to remind you to ask somebody about this. Okay, now let's do a free body diagram in the x direction. Some of the forces in the x direction equals ma in the x direction. And again, because we just want this thing to break loose, at that point the acceleration would be 0 in that changeover region. So let's tabulate all of those things in the x direction. So what we're going to have is the ft cosine theta minus the mu static Fn, and that would be equal to 0. Now we have to expand that quite a bit, so what we're going to end up with is ft cosine of theta minus mu static times Fn, which is from over here, mg minus ft sine theta equals 0. Okay, so let's distribute that mu static through there and rearrange things and see what we can do. So we now have ft cosine theta minus mu static mg. Be careful here because we have a negative mu static and a negative ft. This is going to be plus mu static ft sine theta equals 0. Okay, let's take a look at that and see if that looks good. Okay, I think that looks good. So now what we can do is group the FTs together and factor that out. And you'll see why in a minute, because what we're trying to do here is to isolate these angles. Isolate those angles and get everything else on the other side. Okay, so ft cosine theta plus mu static sine theta. This term here shows up a lot in friction problems, so don't be surprised to see that. Whoops. Then the mu static mg here, just toss that on the other side, mu static mg. Now, let's solve it for cosine theta plus mu static sine theta. So cosine theta or plus mu static sine theta equals mu static mg over ft. Now, how do you find the best angle for this? It's not real easy to solve for theta right there, but there's one little trick we can do, because this, if you recognize it from calc, this is a max-min problem. So if we take the derivative of both sides, then let's see what happens. Okay, so I'm going to change color here. So the derivative of the cosine would be a negative sine theta plus the mu static cosine theta. And since the right side is constant, it goes to 0. Now, what can we do with that? Mu static cosine theta equals sine theta. Mu static equals sine theta over cosine theta. I'm going to bring this up over here. So mu static then is going to equal to the tangent of theta. You've seen things like that before where some of these simplify down to just tan theta. Okay, this is a little ugly. Okay, so what are we going to do? We're going to find the angle. So theta is the angle whose tangent is mu static. So that would be the 0.35 value. We work this out on the calculator, and we come up with 19.3 degrees. So this is our theta max. That is the best angle to pull that at, so you can pull the largest amount of the box and sand without breaking your rope. Okay, so that's the answer to part A. Part B then is pretty simple at that point. What we can do then is go grab one of our equations that we had over there on the other side, or in the other part of the problem, and find something that will let us solve for mg. And that looks handy, so we'll say mg then equals f t sine theta Okay, I was just thinking there's an easier way to do this. We already have an equation where everything is filled out for us. That would be this guy here. So we can just take that, solve for mg. So mg would be equal to ft times quantity cosine theta plus mu static sine theta over mu static again. Okay, let's plug our numbers in and see what happens. We get 1100 newtons times the cosine of our new angle, 19.3 degrees, plus 0.35 times the sine of 19.3 degrees. All of that over 0.35 again. Okay, so grab your calculators, run that through, and see what we get. I'm going to pause here a little to let you catch up on writing. Also, okay, so let's take a look at the answer on the calculator. I got 3330 newtons, and I believe that is the answer on the answer key. Okay, so there we go with problem 17. Okay, man, the next problem was number 39. I'm running short on time here, so I'm going to stop after this one, and I'll continue working on number 43, and I'll upload that shortly after. So partway into the period, that should show up on Haiku Chapter 6 in the right-hand column. Okay, so our given here is 5.4 meters. We've got a cat on a merry-go-round, and that's the radius of the merry-go-round. The period is equal to 6 seconds. And what we're looking for is the minimum static coefficient of friction to keep the cat from sliding off the merry-go-round. Not a lot of information there. So what we need to do is look at it from above and realize that this is the cat, and to keep it going in a circle, we're going to need a radial acceleration. Looking at it from the side, we know that the normal force of the cat, the floor on the cat, would be up, the weight of the cat would be down, and a radial would be in this direction, but this is a free body diagram, so we have to make it a radial force, so F radial. So here's our free body diagram. The radial force is what's going to make it go in a circle, and this would be a radial. Now what we want to do with this, let's just redraw that FR by itself and realize that this FR, there's no such thing as radial force. It has to be supplied by something. It has to be a real force, and that would be a friction force. So this would be a force of static friction. Okay, so let's write F net equals ma, but that's ma radial, of course. And the only force that we have there, of course, is F static. A radial, okay, a radial is equal to v squared over r. Let me move this over here. And v, which we'll put over there, is equal to 2 pi r over t. The squared, of course, is 4 pi squared r squared over t squared. So when we plug that in over here, what we're going to get is m 4 pi squared r, because this r squared over here is going to cancel with this one here, and all we're left with is this. Now what's that F static? That's mu static Fn, but of course we know from looking at our diagram up here, Fn equals mg. I'm just going to take a little shortcut there and cancel the m's. So mu static equals 4 pi squared over, I'll lift up my r, 4 pi squared r, I'll throw up here too, over g t squared. Plugging them in, 4 pi squared. R is 5.4 meters. G is 9.8 meters per second squared. The period is 6 seconds. Quantity squared. And when you run this through on your calculator, you get mu stat equals 0.60 for your coefficient of friction. Let me just check that I got that equation right. T squared. Okay, I'm going to upload this thing now and come back in about 10 minutes or so, and I'll have problem 43 ready to go.